The moment did not happen at a telescope. It happened on a page. A single density versus distance plot published in the Astrophysical Journal in the autumn of 2013, authored by Ryan Keenan, Amy Barger, and Lennox Cowie. The plot showed the number of galaxies per unit volume rising and falling as a function of distance from the Milky Way. Standard cosmology predicted a flat line. The plot showed a trench. Galaxy density near Earth ran roughly half the cosmic average and did not recover to the expected value until the distance reached about 300 megaparsecs, close to 1 billion light-years outward in every direction. The trench was continuous, symmetric enough to be treated as a real structure, and centered near the position of our own galaxy. The paper gave it a name that stuck: the local underdensity. Others began calling it the KBC void, after the three authors. The density profile in that paper was not built from a new observation. It was built from an old one, from data collected between 1997 and 2001 by a survey that had by then been considered finished for over a decade. The catalog underneath the plot was the 2-micron all-sky survey, commonly written as 2MASS. Its galaxy list, the extended source catalog, contained roughly 1.6 million resolved galaxies across nearly the entire celestial sphere. Keenan and his co-authors did not need to build a new telescope to find the void. They needed to ask an old catalog a question it had never been asked directly. How does galaxy density change with distance radially outward from Earth in a wavelength band that dust cannot easily hide behind? The answer came back as a trench that should not exist. The consequential moment for 2MASS, in other words, was not its first light on a mountain in Arizona. It was the moment its archive was used to measure the shape of the space our galaxy sits inside, and the moment that measurement began pulling at the seams of the standard cosmological model. Within 2 years, other groups had begun modeling the trench as a physical structure with gravitational consequences. Within 7 years, a paper by Moritz Hasselbauer, Indranil Banik, and Pavel Krupa would argue that a void of the depth 2MASS's catalog implied could, on its own, produce a meaningful fraction of the mismatch cosmologists were then calling the Hubble tension. The instrument that had been built to catalog stars and galaxies in the infrared had, without anyone planning it, produced the empirical map underneath one of the largest open problems in modern physics. To understand why 2MASS was in a position to do this, it helps to look at what the field had been unable to do without it. Before 2MASS, the census of nearby galaxies rested almost entirely on optical surveys. The Center for Astrophysics Redshift Survey through the 1980s, the APM Galaxy Survey out of Cambridge, later the early data from the Sloan Digital Sky Survey. These projects photographed the sky in visible light at wavelengths between roughly 400 and 700 nanometers. Visible light is what human eyes evolved to see. It is also what interstellar dust most efficiently scatters and absorbs. The Milky Way's own disk is packed with such dust, concentrated along the plane of the galaxy, and any telescope on Earth looking outward in visible light must look through it. In the directions where the dust is thickest, the strip of sky within roughly 10 degrees of the galactic plane, background galaxies simply vanish behind the curtain. Astronomers have a term for this obscured strip, the Zone of Avoidance. In the optical, it hides roughly 20% of the extragalactic sky. A 20% gap in coverage is not a rounding error when the question being asked is whether the universe looks the same in every direction on the largest scales. The cosmological principle, the assumption underneath essentially every model built since the 1920s, requires the universe to be statistically uniform once one averages over sufficiently large volumes. Testing that assumption requires counting galaxies in every direction with the same sensitivity. Optical surveys could not do that. They could count carefully in the directions the dust allowed, and they could estimate what might be hidden in the directions it did not. But the estimate itself carried the uncertainty. Any claim about large-scale isotropy built on optical data alone was, in effect, a claim with a 20% blind spot. The problem sharpened through the 1990s and into the 2000s as a second, separate line of evidence began producing numbers that refused to reconcile with the first. The Cosmic Background Explorer satellite, launched in 1989, and then the Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the cosmic microwave background, the ancient thermal radiation released roughly 380,000 years after the Big Bang. From the tiny temperature fluctuations in that radiation, cosmologists could calculate what the expansion rate of the universe, the Hubble constant, ought to be today. The number that came out was consistently in the range of 67 kilometers per second per megaparsec. Independently, teams measuring the expansion rate using nearby exploding stars, type Ia supernovae, calibrated against Cepheid variables, were arriving at a different number, closer to 73. The two methods disagreed by nearly 9% and refused to converge no matter how many times the measurements were refined. The Planck satellite, launched by the European Space Agency in 2009, tightened the cosmic microwave background number to a precision that made the disagreement impossible to dismiss as instrumental error. Planck's final results, published in 2018, delivered a Hubble constant of 67.4 kilometers per second per megaparsec, with error bars small enough that the local supernova value stood clearly outside them. Something had to give. Either one of the measurement chains had a hidden systematic error nobody had yet identified, or the universe was not quite behaving the way the model predicted, or, and this possibility began to be taken seriously around the same time, the local measurement was correct for the local region, but not for the universe as a whole. If Earth happened to sit inside a large, underdense pocket, nearby galaxies would drift outward faster than the cosmic average, and any expansion rate measured from those nearby galaxies would come out too high. The local number would be right. It would simply be describing a local effect. Testing that possibility required something optical surveys could not deliver: a clean, uniform, all-sky galaxy count that did not lose 20% of the sky to dust. It required a census taken in a wavelength band that dust does not easily scatter. Dust grains in the interstellar medium range from roughly 1/100th to 1/10th of a micrometer in size. Light with wavelengths comparable to those grains scatters strongly. Light with wavelengths substantially longer than those grains passes through with much less loss. Near-infrared light, in the range from about 1 to 2.5 micrometers, sits in exactly the window where dust becomes semi-transparent. At the K's band, near 2.17 micrometers, extinction through the Milky Way's disk drops by roughly a factor of 10 compared to visible light. The zone of avoidance narrows. Galaxies behind the dust become visible. The specification was demanding, but by the middle of the 1990s, the pieces had reached the point where a team could realistically assemble them. The project that took the specification and turned it into a functioning survey was led out of the University of Massachusetts Amherst, with Michael Skrutsky as principal investigator, in partnership with the Infrared Processing and Analysis Center at Caltech, where Rak Kutri would eventually oversee the data pipeline. Funding came from NASA and the National Science Foundation. What they built was not a single instrument, but a matched pair: two telescopes with identical optics, identical detectors, and identical observing procedures, placed on opposite hemispheres so that between them they could see the entire sky. The Northern Telescope sat on Mount Hopkins in Arizona, on the ridge that also holds the Fred Lawrence Whipple Observatory. The Southern Telescope sat at the Cerro Tololo Inter-American Observatory in the Chilean Andes. Each had a primary mirror 1.3 meters across, modest by the standards of research astronomy even at the time, but sufficient for the survey's purpose. Depth was not what the project was trading for. Coverage and uniformity were. A telescope that photographed the entire sky twice, once from each hemisphere, in 3 identical near-infrared bands, would produce a catalog whose statistical properties were the same in every direction. That uniformity was the point. Any anomaly the catalog eventually revealed could be trusted as a property of the sky, not an artifact of the instrument. The 3 bands were chosen for their positions in the near-infrared atmospheric windows, the wavelength ranges where the atmosphere is transparent enough for ground-based observation. J-band centered at 1.25 micrometers, H-band at 1.65, K's band at 2.17. The K's band in particular was engineered slightly shorter than the standard K-band, cutting off before the thermal emission from the atmosphere and telescope began to overwhelm the signal. At each of these wavelengths, the detector had to see faint galaxies against a sky that itself glowed, and it had to do so without contributing its own thermal noise to the image. The solution was cryogenic. The detector arrays were cooled with liquid nitrogen to roughly 77 Kelvin, around -196 degrees Celsius, reducing their dark current to a level where the actual sky background became the dominant source of noise. The detectors themselves were NICMOS 3 arrays, developed originally for space-based astronomy and adapted for ground use. Each was a 256 by 256 pixel grid of mercury-cadmium telluride, an alloy semiconductor whose bandgap can be tuned by adjusting its composition to make it sensitive precisely in the near-infrared window the survey needed. 3 such arrays sat inside each telescope's camera, one behind each of the J, H, and K's filters, imaging the same patch of sky simultaneously through a dichroic beam splitter arrangement. Every galaxy the survey saw was therefore measured in all 3 bands at once, producing a color as well as a brightness, the color itself later useful for distinguishing genuine galaxies from foreground stars and for estimating rough distances. The observing strategy was equally deliberate. Rather than pointing at one patch of sky, exposing for a fixed time, and then slewing to the next, the telescopes operated in a mode called freeze-frame scanning. The telescope drifted at a slow, constant rate along a strip of sky. The detector read out every 1.3 seconds, capturing a fresh image as the sky moved across it. Each point on the sky was thus imaged 6 times during a single pass, with the images stacked to build up the equivalent of a 7.8-second exposure. The scanning motion covered a strip roughly 8.5 arc-minutes wide and 6 degrees long, and the 2 telescopes together completed roughly 2,000 such scans per clear night. Between 1997 and 2001, the Northern Telescope operated for over 1,100 nights, and the Southern for over 1,100 more. The final catalog covered 99.998% of the celestial sphere, effectively everything except a handful of small regions near the galactic center, where crowding from foreground stars defeated the source extraction algorithms. What came off the telescopes each night was raw imagery, some 4.1 million frames across the survey's lifetime, and every frame had to be corrected before anything astronomical could be extracted from it. Airglow from hydroxyl molecules in the upper atmosphere produced a background that varied on scales of minutes. Thermal emission from the telescope structure itself added a slow drift. The moon, when above the horizon, scattered light across the entire field. Occasional satellite trails cut bright lines across the frames. Cosmic rays struck the detector arrays at a rate of several per minute, depositing spurious signals that had to be flagged and removed. The data pipeline at Caltech ran a sequence of calibrations: dark frames subtracted, flat fields divided out, sky background modeled and removed on a per-frame basis, then astrometric registration against known reference stars to place every pixel at a precise position on the celestial sphere. Only after that pipeline was the source extraction run. 2 catalogs came out of it. The point source catalog listed everything the detector saw as unresolved: stars, distant quasars, the vast majority of what fills a near-infrared image. It contained roughly 470 million objects. The extended source catalog listed everything the detector saw as resolved: objects whose light profile was broader than a point, meaning they were nearby enough that their intrinsic size exceeded the atmosphere's blurring. This catalog contained roughly 1.6 million galaxies, and it was this catalog that would become the empirical foundation for the void discovery. The extended source catalog reached a depth of magnitude 13.5 in Ks band, bright enough to include galaxies out to redshifts of roughly 0.1, corresponding to distances up to about 400 megaparsecs. That was the volume within which any local underdensity would be measurable. The catalogs were released to the public in stages. A first release of preliminary data came out in 1999. A second, larger release followed in 2000. The full and final all-sky data release arrived in March of 2003. From that point onward, anyone could download the catalogs. What they contained was, in effect, the first uniformly calibrated, near-infrared map of the resolved extragalactic sky. The zone of avoidance had shrunk. Galaxies that had been invisible behind the dust in optical surveys appeared in the K's band imagery, some for the first time. The southern sky, historically less well studied than the northern, now had the same depth of coverage as the north. The Keenan-Barger-Cowie analysis of 2013 worked directly from this catalog, cross-matched against redshift surveys that had by then measured distances to a large subset of the galaxies. The 6-degree Field Galaxy Redshift Survey, completed in 2009 at the Anglo-Australian Observatory, had measured redshifts for over 100,000 galaxies in the southern sky. The Sloan Digital Sky Survey provided similar coverage in the north. Combining these redshift measurements with the 2-mass extended source catalog produced a 3-dimensional map, galaxies with positions in the sky from 2-mass and distances from the redshift surveys. Keenan and his co-authors then binned the galaxies into radial shells outward from Earth, counting the number of galaxies per unit volume in each shell, and comparing that number to the cosmic mean predicted by standard cosmology. The trench in the resulting plot began within the first 50 megaparsecs and did not close until roughly 300 megaparsecs outward. At its deepest point, the galaxy number density ran 46% below the cosmic mean. The paper reported this as a 6 sigma statistical deviation from the density expected under a homogeneous universe, a level of significance normally treated in physics as beyond the threshold for coincidence. The trench was too large, too deep, and too centered on our own position to be dismissed as a statistical fluctuation. That the trench was on the plot did not mean the plot could answer every question asked of it. The catalog underneath the KBC analysis had limits, and those limits set the terms of the argument that followed. The magnitude 13.5 cutoff in Ka's band, which had defined the extended source catalog's depth, translated into a reliable galaxy census out to redshifts of roughly 0.1, distances of about 400 megaparsecs. Beyond that, the survey's completeness fell off. Fainter galaxies at greater distances slipped below the detection threshold, and the fraction of the true galaxy population being counted began to drop. This mattered for the void measurement in a specific way. The trench in the density profile had to be measured against a baseline, the cosmic mean density, and that baseline had to be established using the same catalog, at distances where the void's effect had faded. If the catalog's completeness was itself changing with distance, the shape of the trench could be distorted by the very tool measuring it. Keenan and his co-authors had corrected for this. The correction relied on models of the galaxy luminosity function, the statistical distribution of galaxy brightnesses in the universe, extrapolated to account for what the survey was missing at the faint end. The corrections were standard, defensible, and applied consistently. But they were corrections, not direct measurements, and any group revisiting the analysis with different assumptions about the luminosity function could arrive at a different density profile. This is what happened. In 2014, Nigel Whitbourne and Tom Shanks at Durham University published a reanalysis using a slightly different catalog combination and different completeness corrections. They found a local underdensity, but a shallower one, closer to 15 or 20% below the cosmic mean, rather than close to 50%. The trench was still there. Its depth was in dispute. Further analyses widened the disagreement rather than resolving it. In 2022, a team led by Wang at the Chinese Academy of Sciences applied a peculiar velocity technique, inferring the void's presence and depth from how galaxies were moving rather than from how many were being counted, and found evidence for an underdense region roughly 1/10 the volume Keenan had originally proposed. The peculiar velocity method used different data entirely. The Cosmic Flows 4 Catalog of Galaxy Motions, published by Tully and collaborators in 2023. What the disagreement between the two methods revealed was not that one team had made a mistake, but that the void's true parameters, its depth, its exact boundary, its precise centering on the Milky Way, could not be fully resolved from the data 2-mass had left behind. The instrument had reached its limits. Those limits had specific structural sources. First was sensitivity. The 1.3-meter apertures on Mount Hopkins and Cerro Tololo were not chosen for deep imaging, and the survey traded depth for coverage from the beginning. Any galaxy fainter than magnitude 13.5 in K's band was invisible to it, and the majority of galaxies in the universe are fainter than that. Second was the residual zone of avoidance. Near-infrared observation had narrowed the dust-blocked strip along the galactic plane compared to optical work, but had not eliminated it. Roughly 10% of the sky remained sufficiently obscured that source extraction became unreliable. The crowding of foreground stars, combined with residual dust extinction, produced regions where the catalog could not be trusted to count galaxies accurately. Statistical modeling could estimate what was hidden there, but the estimate carried uncertainty, and the void's true geometry depended on the sky the survey could not see clearly. Third, and structurally the most important, was that 2MASS did not measure distances. It was an imaging survey. The three-dimensional density map underneath the KBC analysis had been built by cross-matching the extended source catalog against redshift surveys conducted by other instruments. Every distance in the profile came from a separate spectroscopic measurement taken years after the 2MASS photometry, using different telescopes with different selection functions. The 6-degree field galaxy redshift survey had targeted its own subset of galaxies according to its own criteria. The Sloan Digital Sky Survey had done the same. Combining these catalogs with 2MASS produced a hybrid dataset whose statistical properties were not fully uniform, and the void's measured shape inherited every selection effect from every survey that contributed a distance. The 2MASS team had been aware of the distance limitation from the beginning and had proposed a spectroscopic follow-up program to address it. That program became the 2MASS Redshift Survey, abbreviated as the 2MRS, led by John Hutra at Harvard until his death in 2010, and completed by Karen Masters and collaborators in 2011. The 2MRS used a network of moderate aperture spectroscopic telescopes to measure redshifts for roughly 44,000 nearby galaxies drawn from the 2MASS extended source catalog, producing the first uniform spectroscopic map of the local universe out to redshifts of about 0.03. It remained, more than a decade after its completion, the standard reference for testing cosmological models against the actual local structure of galaxies within roughly 100 megaparsecs. But its depth was even shallower than the imaging survey it drew from, and it could not extend the void measurement outward. Resolving the disagreement between the Keenan and Whitbourne analyses and between the number count method and the peculiar velocity method required a different instrument. It required an instrument that could image and measure distances simultaneously, at depths reaching well beyond the 2MASS cutoff, with uniform selection across the entire survey volume. That instrument now exists. It is called Euclid, and it was launched by the European Space Agency in July of 2023 from Cape Canaveral aboard a Falcon 9 rocket. It reached its operational position at the second Lagrange point of the Sun-Earth system, roughly 1.5 million kilometers from Earth, in early 2024. Its science mission began that February. Euclid carries a 1.2-meter primary mirror, slightly smaller than the 2MASS apertures on the ground, but operating in the vacuum of space, above the atmosphere that had forced the ground-based survey to cool its detectors and scan through airglow. The mission has two instruments sharing the focal plane. The visible instrument, known as VIS, takes broadband optical images at wavelengths between 550 and 900 nanometers, at a resolution fine enough to measure the shapes of distant galaxies for weak gravitational lensing analysis. The near-infrared spectrometer and photometer, known as NISP, images in three near-infrared bands centered near 1.1, 1.4, and 1.7 micrometers, and simultaneously performs slitless spectroscopy across the same field. That combination, imaging and spectroscopy on the same field at the same time, is what the KBC problem specifically needed. Every galaxy Euclid detects in imaging gets a redshift from the spectroscopic channel of the same instrument, without the selection function mismatch that came from stitching separate surveys together. The wide survey plan covers approximately 14,000 square degrees of extragalactic sky over the mission's 6-year primary phase, reaching depths sufficient to catalog galaxies out to redshifts of roughly 20 times the redshift reach of the 2MASS extended source catalog. A separate deep survey covers roughly 50 square degrees at magnitudes fainter still. The stated cosmological objective, laid out in the mission's definition study report, published in 2011 under René Lorais as project scientist, is to measure the geometry and growth of cosmic structure with sufficient precision to distinguish between competing explanations for both the accelerating expansion of the universe and the local anomalies that surveys like 2MASS had left unresolved. The first substantial data release from Euclid, known as the Q1 release, came in March of 2025. It covered 63 square degrees of the deep survey fields at approximately the depth planned for the final wide survey, and it contained early catalogs of galaxies, quasars, and gravitational lens candidates. The Q1 release was calibrated astrometrically against the 2-micron all-sky survey point source catalog. This is the specific mechanical dependency worth noting. Every position measured by Euclid, every galaxy Euclid catalogs at its far greater depth and precision, is placed on the sky using reference stars whose positions were fixed by 2MASS between 1997 and 2001. The 1.3-meter telescopes on Mount Hopkins and Cerro Tololo had been decommissioned as survey instruments long before Euclid launched, but the catalog they produced had become the coordinate system. This is what 2MASS is currently doing. It is not observing, it is being read from. The point source catalog remains the standard astrometric reference for large area surveys operating in wavelengths from the optical through the near-infrared, calibrating not only Euclid, but the Vera Rubin Observatory's LSST commissioning data, the Roman Space Telescope's early mission planning, and the ongoing DESI redshift survey. The extended source catalog remains the empirical baseline against which claims about the local galaxy density distribution are tested. The 2MASS redshift survey continues to serve as the standard local universe map for peculiar velocity studies and for the validation of large-scale structure simulations. The trench in the plot from 2013 has not been resolved. Euclid's wide survey, still years from completion, will settle whether the void is as deep as Keenan's original analysis reported, as shallow as Whitbourne's reanalysis found, or something else entirely. The final Data Release 3, currently scheduled for the end of the decade, will produce the first fully self-consistent three-dimensional map of the local universe at the depth and precision the question requires. Until then, the answer sits where it has sat since 2013, inside a catalog compiled from 4.1 million exposures taken during 1,100 nights on 2 mountains, by an instrument that had been built to see what dust had been hiding, and had, in seeing it, mapped a hole no one had asked it to look for.